Well, welcome. In this video we're going to be looking at lesson 6.3, which is all about natural logarithms. And the one thing you'll be learning about in this video is the fact that a natural logarithm is an inverse for a function where we have e to the x power. So that's going to be a key component. And another thing that we'll be looking at in this video is how to solve an equation using natural logarithms. So why don't we go ahead and get started by making sure we can define what a natural log is and how it really is the inverse of a function in the form e to the x. So let's get started.
Okay, so let's recall what we remember about inverses. Now remember, inverses, they basically undo each other, or remember that with an inverse the domain and range switch. And so when we're dealing with logarithms and we're dealing with an exponential function like e to the x power, the natural log is the inverse of that function. Now, the notation for the natural log is, again, we use the inverse of f symbol. And what the symbols that we use, though, for the natural log is ln of x. And again, the natural log of x is the inverse of e to the x power. So, even without knowing what the graph looks like, if we know that e to the x power looks like this graph here on the left, here in red, the inverse would be a reflection across the line y equals x. And that's what that dashed line is. That's the line y equals x. So to sketch a graph of what the inverse would look like, we would just flip or reflect that line, the red line, over the line y equals x, and we'd get something like this green line. Now, basically a natural log, what you need to know about that is it's just a log function with the base of e. Okay? We don't actually have, just like when we have log base 10, we don't write the 10 down, because we recognize when we see the log of 7, for example, we know that it's a common log. The base is 10. It's not needed. So when we're dealing with the natural log, you just need to understand that the natural log is where we have a logarithm with a base that's e. So that summarizes the fact that e to the x and ln of x, the natural log of x, are inverses of each other. So let's look at some more properties of the natural log function. So here's a graph of the natural log function. So what I want you to do is I want you to look at this graph, and I want you to see if you can determine which one of these represents the domain and range of that function and what the asymptote of that function would be. So go ahead and pause the video and see if you can narrow it down to which one of those four the correct answer would be. Okay, let's see how you did. You should have got that this last one would be your correct answer, because the domain starts from 0 and it goes on to infinity. The range goes from negative infinity to positive infinity, and it's got a vertical asymptote, so vertical asymptotes are in the form of x equals something, and it's a vertical asymptote at x equals 0. Now, remember last chapter we talked about compound interest, and we had that formula we call PERT, principal times e, and then our exponents r times t, where the r is your rate and the t is your time. We could use that to determine how much money is in your account that is compounding at an annual interest rate after t years. So let's review. If you had an interest rate of 4.5% compounding continuously, how much money would you have if you invest $1,000 for 10 years? So what we would do is we would just take that information, we'd put it into our equation. Now the key to remember, though, is that our rate, 4.5%, is a decimal 0.045. And now you can just plug in your calculator, and it's really easy to do, and you get an answer of $1,568.31. Now, what if we want to figure out the time it would take for an investment to grow to be a particular value? So, for example, let's say if we have $1,000 at 4.5%, again, annual interest, compound continuously, we want to figure out how long it would take for that to grow to be $10,000. Well, the first step in solving something like this is we're going to put it in that PERT formula, but our t is our unknown. Our t is our variable that we're going to have to solve for. And the one thing that we're going to have to do here is the next step is to isolate the exponential. So we're going to take that e to the 0.045 t power. We want to get that by itself. And I would do that by dividing both sides by 1,000. And when you do that, so when we do that, we would get e to the 0.045 t equals 10. Or, like we say in the next paragraph here, we have 10 equals e to the 0.045 t. Same thing. So if we wanted to solve this, the next step would be to put this in logarithm form. Now you could use the triangle of power to help you out, and you can see the triangle of power is set up there for us. So we would have our base would be e, and then we would have 0.045t as your exponent, and 10 is our value. So the way we could write that out would be log base e of 10 equals 0.045t. Because remember, all logarithms, the exponent is what it equals. Now, but remember from the beginning of this lesson, log base e is the same as the natural log. So this would be our answer. So natural log of 10 equals 0.045t. So now that we have it written in logarithm form, we're going to solve that logarithm equation. So if we have the natural log of 10 equals 0.045t, to solve that equation, we would just divide both sides by 0.045. And when we take the natural log of 10 divided by 0.045 on your calculator, you get your answer of 51.2 years. Now this process we went through can be done by simply following these 4 steps. So the first step is going to be to write out the equation. So we're going to take and plug it into the information that they give us and put it in that formula for PERT. And once we have that equation, one of the variables are usually going to be the exponent, probably your time. And so we're going to have to isolate the exponential piece. And once we get that piece by itself, then we're ready to do this third step, which is to convert to logarithm form. Once we have it converted to logarithm form, we can go to the last step, which is just to solve for the variable. So if you follow those 4 steps, like we did going through this problem, you'll find that these exponential or these logarithm equations are actually rather simple to solve. So let's look at another example together, and then I'll have you try one on your own. So let's look at this one. It says you invest $100 in an account that collects 7.35% annual interest, compounding continuously. How long does it take for you to have $150? Well, when you hear that phrase, compound continuously, again, that's the giveaway that we're going to use PERT. And the rate, 7.35%, we have to change that to a decimal of 0.0735. And our $100 is going to be our principal. That's going to be our P. So our equation will be set up like this. Now, that's our first step. The second step is to isolate the exponential. So that means we want to get the e by itself. I'm going to do that by dividing both sides by 100. So now I have e to the 0.0735t equals 1.5. So now the next step is to convert this to logarithm form. So this would be a log with a base e with a value of 1.5 equals our exponent. But a log base e, remember, is a natural log. So it would be the natural log of 1.5 equals our exponent of 0.0735 times t. Now all we have to do to solve this is to divide both sides by 0.0735, giving us the natural log of 1.5 divided by 0.0735, or 5.5 years. So that's how you can do that problem. Okay, I want you guys to try one on your own. So I want you guys to try this next one, where you're borrowing $200,000 for a house at 5.75% annual interest, compound continuously. Want to figure out how long does it take for your loan to be worth $1 million. And we're going to go ahead and round to the nearest year for this problem. So go ahead, pause this video, and press play when you're ready to check to see if you have the correct answer. Okay, how'd you do? Well, let's find out. So your first step would be to set this up into our equation. And when you do that, we get 200,000 times e. Your exponent's going to be 0.0575t equaling $1 million. So we want to isolate the exponential piece, so I divide both sides by 2,000, so you should have gotten 5 when you did that. When you put this in logarithm form, you'd have the natural log of 5 equals 0.0575 times t. Divide both sides by that 0.0575, and we get approximately 28 years.
Well, that's it. Hopefully you understand now how to use natural logarithms, both as the inverse of e to the x power, and also how to set them up and how to use them when trying to solve an equation. So with that, good luck now as you work on your assignment.